Good afternoon, everyone, and welcome to this talk on persistent memory and computational storage. This is a SNIA industry update, and I'll be talking about what's happening from the SNIA's point of view. What's the industry doing? What are the standards? What are the key components that you should know in the different models that are there for programming a persistent memory? And also, I'll touch upon a little bit on computational storage. So that's more of again, an industry update. So this will give you a kind of overview of what's happening in the industry, what you should care for, how it is getting standardized, what are the different APIs that you should be bothered about, right? So before I start off this, I just want to know one thing. How many of you are developing applications for persistent memory? Just a show of hand in the sense you are involved or you are trying to use it or trying to evaluate it. Okay, few people, good. So I'll start by saying my personal experience on persistent memory, right? Way back in somewhere around 2014, when persistent memories were being talked about in the research labs, these are the storage class memories, right? And they are at the same speed at which the DRAMs work, and they also have the persistence, right? This was kind of a big change, right? We are always used to writing the programs in a way where we know that whenever I write something, it goes into the volatile memory. That's the first place where it resides. And then beyond that point, you always flush it. As a storage developer, everybody knows that we have something called flush. That's when it goes to the disk. So this changes in the persistent memory, right? It's a single, one instruction can do both. Put it onto the memory and it is almost persistent there. So we were trying to do this, trying to evaluate this, right? And first thing that we were doing was writing persistent indices, right? For any database application developer might know this. Persisting indices in memory for any in-memory database is a huge advantage, right? When the system goes down, it comes back, you already have the indices, you don't have to rebuild that, right? So we were trying to do this, and during those days, none of the things were there for us, as in if you want to use that, you will have to write your own memory allocator, you will have to write your own flush mechanisms using the existing whatever that was there. So we started off writing this B plus tree. We wrote the B plus tree, persisted on the persistent memory, and now you can imagine when you persist a B plus tree, and the records can go into millions, right? It could be few millions, right? When you build the indices. And when you make a small update within the persistent memory, you're almost like going bottom of the B plus tree and make a small update. And if you forgot, or if there is an error in updating your pointer, then the entire B plus tree is corrupt. And tracking that, going down, all the way down, tracking that, it's a hard problem to solve, right? Now once you have that, you have a persistent B plus tree. Let's say that you harden the code for some time. Now how do you integrate that with the application which is trying to use this, right? There should be a nice way to seamlessly integrate this code, right? If you don't have a seamless way of integration, then what happens is that if something corrupts, you don't know which the application is at a fault or your B plus tree is at a fault. So you have all those problems, right? So I'm talking about the same thing here today. The SNIA twig, persistent memory twig, has done a lot of work from the last few years, and it has made all these libraries available for you to use them as a developer through the nice interfaces, nice APIs, and we will talk about that now today. Okay. So these are some of the things that I will cover. What are the different programming models that you have for persistent memory, and what you should know at a developer level, like what you should know about the persistent memory, the characteristics that it exposes, okay? And often, how do you use this? You want to use the persistent memory with some application modifications that I was referring earlier, or you would like to use it as a POSIX APIs. I am comfortable with POSIX APIs. I am comfortable using POSIX APIs. Behind the POSIX API, let me have my persistent memory. I don't care, right? So that's another model. So these are the two different models, and we will talk about that, each one of them. And then the learnings, right? Over the period of time, what learnings we have. And where are we heading to with this? Now, having said that you have a persistent memory on your system, what could be the possible things, and where is the SNIA heading towards? So these are some of the things I'll cover in persistent memory. Then I will touch upon the computational storage, right? Now, from morning you have been hearing about a little bit about computational memory, right? There was a talk from PhonePe who talked about computational storage, and there was a Professor Gopinath identified the data-centric compute, right? Now, at a first level, I also felt that both look similar. What's the difference? It's a faster way of accessing things, right? There are differences. People who know it, there are architectural differences are there. And from a developer point of view, how do you identify that I need a persistent memory that I need to be using, or should I be going for the new model of computational storage? So these are some of the things that I'll touch upon, okay? And so when you have this a change of this nature, a two-level persistent model from taking away from that, and you have a single level of persistence, right? When you have such a big change, right, it's a complete ecosystem of people who are involved in this. One is, these are the guys who are providing some of the hardware, right? You can just read the names here: Micron, Gigatech, SK Hynix, Viking, and others. So these are all the ones who are providing you the non-volatile memory, persistent memory DIMMs, right? And on the other side, these are the server vendors who are putting those memory modules into the system and offering you as the complete server storage. And on the software side, you have operating systems being enhanced for making them aware of persistent memory, right? And on the other side, SNIA and JDEC are involved in developing the standards for that. Why do you need the standards? If you have if you're trying to build anything, a system component at the hardware level, you can be very proprietary and have your own way of defining that. But if it doesn't integrate with other components, with the common set of APIs, right, then it becomes very tough for others to work interoperably with that system. So you need a kind of standards being defined for all those things, which becomes very easy for people to consume that, right? And just to touch upon what JDEC is doing, JDEC is the Semiconductor Association which is defining these standards. On the left hand side is the NVDIMM N, NVDIMM persistent. NVDIMM N is the basic difference is that there is a DRAM module, it's a DRAM, and behind that the flash is sitting. The flash acts as a persistent memory, but what the end user sees is that's exactly like a DRAM, right? The persistence is being given by the flash, so it has a certain characteristics. Since it's exposed as the DRAM, the latencies are around exactly like DRAM, and its age is also equivalent to the DRAM. And on the other side, you have the NVDIMM persistent, and this is where all the characteristics of storage class memory are being filled in. There is no, the DRAM itself is not there, but it's a persistent memory that's being exposed, which is slightly slower than 4 to 5x times slower than the DRAM, and that's the one on the right hand side. But the complete standards for NVDIMM N are already available from JDEC. The NVDIMM P is being developed, and that's something would come in the second half of 2019. Okay. Now, I gave you some story about the way we were trying to do. as to take advantage of the persistent memory. So here are a set of some of the use cases. So when you have a persistent memory, the in-memory database are the bigger targets, right? Now you have in-memory databases which span across 4 to few terabytes of data. Entire data set is in the memory, right? So those are the first targets, because persistent memory comes with a higher capacity in the same form factor, and those are the first guys to use it. And then they are the ones to exploit it to the maximum extent. And so it's a log acceleration they can do, in-memory commit. And in the previous talk also someone was talking about memcached, right? So memcached is just basic, it's a read cache. It's a server, right? Hosting a lot of data set. And those are the targets. And that's something that can be utilized here. We'll talk about that. And then the file system, fast caching. So when you have a file system, and then when you moved away from earlier days of disks to flash, you would have seen the flash giving you much better performance. When you consider the latency, when you consider the IOPS that you get. So you moved from a disk-based system to the flash, you got much bigger performance benefit, right? So you will see the same effect here also. When you move from flash, which is in few hundreds of microseconds, to NVDIMM persistent memory, which is in nanoseconds, you will see again a jump in performance. Does that make sense? Right? So you will see a similar performance. But there is a glitch, right? When you make your persistent memory, when you make your storage so fast, what happens to the next thing? Your software starts becoming a bottleneck, right? You moved from disk system, you built applications for disk system, you moved to the flash, you saw some benefits. Now you moved from a flash system to the persistent memory. You will see some bottlenecks creeping up in your software, and that's the thing that engineering somebody has to do if you opt for utilizing in that way. So these are other use cases, virtualization, and virtualization is a very good classic case, because when you virtualize entire bare metal system, right, hypervisor sitting or even microservices world, the idea is that you utilize it you consolidate a lot of VMs within that, and then the typical IO blender problem starts coming into picture, because a lot of VMs are doing IOs in a different way. So that's where persistent memory could give the boost for that. And big data, cloud computing, IoT, artificial intelligence, these are all analytics workloads which can take benefit of that. So these are some of the applications. So what you should know, its persistent memory is exactly like a memory. You could use it as a load and store with the load and store instructions, and it also has persistent characteristics, and exposed to the applications using SNIA Twig APIs. We will talk about that. These are the things that are available today for you to start experimenting with this, utilizing that, move your application from traditional way of using it to the new world where you can benefit from the persistent memory. Persistent memory, they are actually, the density is almost like 4x from typical DRAM. It starts from 32 gig, goes all the way up to 256 gig. So you have bigger, if you can understand, if you can just remember the density, right, it's almost like 4x. So lot of, in a same DIMM module, you can put a lot of memory. That's the advantage you get. And point here is that when you ask that question, if somebody is thinking from a memcached perspective, right, he would go for that. I'll explain that. Cost, see, at present, the numbers, I don't have it. Recently, Intel has published some of the numbers, but again, it's not clear as to what would be the cost. But the benefits of persistence and the density, it could be a little bit more than what the DRAMs could have. Yeah. Yeah, exactly. Sure. Sure. Yeah. Cost, I wouldn't say that it would be cheaper, but because when you have so much of new things coming in, the architecture of the entire system changes. But I don't have the numbers, sorry. But we expect to improve. At some point of time, there will be inflection point where you will see that using a persistent memory as a volatile memory is better than having just the DRAM. Makes sense, right? Yeah.
Of SSDs expanded with the TLC coming into picture, right? Do you see a similar trend possible in persistent memory in the future?
What's the word you mentioned? DAX.
Sorry?
What is that used?
With the triple layer consistency on the multiple cells and triple cells.
Okay.
So, do you see a similar trend that is expected with the increase in adoption of persistent memory decreasing the cost factor?
Yeah. See, you're asking the way they increase the density in the flash. Is it much similar way in anyone in the persistent memory? That depends on the kind of persistent memory that you are exposing. In the first slide, I showed you the JDEC where you had NVDIMM N and NVDIMM P. The P is the storage class memory, and depending upon which storage class you use, it depends whether you can increase the number of cells per within a form factor. But it is possible. In the initial versions, you will see a lesser density, but as you move forward, as the physics intricacies are solved, it will be higher. But at the first level itself, in the generation 1, you could say it is almost like 4x increased. Right? Okay. So what isn't persistent memory? So it's not like persistent memory only talks the blocks. It is like a memory access, and it's not. And you can't say that I have a kind of a storage on which I can do load and store, and it completely hogs the system, right? It's not that. Okay, and so here is the programming model that we should be bothered. If anybody is in this room is looking for playing around with this, this is what you should be looking, right? So here, what you see here is a persistent memory, and which is being exposed, handled by the NVDIMM driver, handling the intricacies of all the persistent memory. And here is a file system, and other way is to expose it to the application directly, right? Now, if people want to see quick benefit, I want to see what's the impact of my on my applications from the persistent memory. You could use it like a typical SSD. Put the persistent memory behind a file system, or as a block device. It could be used as a standard SSD. And if you're using behind file system, then it's POSIX compliant, right? So this is the first way to use it, and see if there is a benefit. Now keep in mind that I told you earlier that if the storage is so fast, you will start seeing the bottlenecks creeping up in your application, right? Especially when you have queues, queuing, dequeuing, all those things will start seeing some bottlenecks. Now, if these bottlenecks in the software are so high that if you enter into 100 microseconds, 100 microseconds, that area, then you are almost going into the flash area now. Then you wouldn't be exploiting the benefits of persistent memory, right? All the benefits is being killed by the application bottlenecks, which is more than 100 microseconds, right? You're almost like better using the flash instead of persistent memory. And yeah. Yeah, so when you access through file system, right?
Yes.
It's exactly like the way you write your other
No,
applications.
but in the file system, once for example, Linux file system, do we need to have a separate APIs which will be used to access the NVMe DIMM?
No, it's the same APIs, because when you have application directly talking to the file system, right?
Yes.
So application will never come to know what is below the file system.
No, but how about the file system? So file system needs to have the capability to access.
When file system talks to the device, the
Yes.
NVDIMM driver, it's a block device interface. It will talk to him as a block device. Now, if you want to make aware of, like the file system knows that this is a persistent memory that I want to take some characteristics advantage of this, that's where you fall into this category, PM aware file system. Now, typical file systems work in a page cached mode, right? You write something, it goes into the page cache, and it's a dirty cache. Let's say you write it, and only when you flush from dirty cache, it will go to the media. But in this case, when you say PM aware, means he knows that I don't have to do a page cache, I'll directly write it into the persistent memory file system. So that's a DAX access, direct access. So there is no page caching, it directly goes to the persistent memory. And so these are the two ways in which you can use the, as you brought out the PM aware file system. In Linux, there are some versions that are available. NOAA is a file system. Earlier it was Intel released a persistent memory file system. Those are all available for you to experiment. And then I'll talk about certain ways that you can use in the programming model, okay? Yes. It will be possible. As long as you maintain the, if you are using the POSIX, you will always do flush and wait for the confirmation of the flush coming back, right? And you will always wait for that. Now, if you are using in a model where you want to take care of how you want to lay out on the persistent memory, then you are responsible for recovery. I'll touch upon that also.
Okay.
So this is another volatile capacity. In this mode, you use the persistent memory as a volatile memory because of its density. As I mentioned, memcached is one of the target, right? It hosts a lot of large capacity of data sets for read cache. Now you can use the persistent memory because of its higher density. You can put a lot of memory inside a server and then use it. And when the system reboots, you just throw away whatever that was there. So it will act like a volatile memory. That's one way to look at it, right? So, so these are the different ways to use the persistent memory with no application modification. PM as a fast SSD, PM as a direct access, the PM aware file system where you don't have any page cache, directly writing into the persistent memory. So that actually brings in, removes some of the bottlenecks that you will have in the file system itself when you write directly, right? And use it as a volatile memory. Now, so this is often some of the things that are forgotten is this mode, right? When application wants to utilize the persistent memory in a way that it wants to have a complete control over the persistent memory, how he wants to lay out the data, how he wants to read the data, how he wants to maintain the consistency within that persistent memory. In this mode, it is the fastest because in this mode, you are almost using like load and store. The way you access your DRAM, it's the same model. You say when you write a program, A equals to B plus C, you're writing into the A, that A is nothing but a resistor in the writing into the persistent memory. So any operations that you do and call a flush means it's already there in your persistent memory. There is no other explicit flushes that you call like in a typical POSIX programming. So this is the fastest model, but this needs a lot of programming changes in your code, and how SNIA has worked within the twig to make you available of some of the libraries within this. I'll show you that now. So here is the PMDK. On this side, you see the persistent memory development kit. It's in a red box. That's a persistent memory development kit. It's available over the GitHub. All these libraries are available for anyone to use them directly with the application. As I mentioned, when you want to handle the persistent memory, you need a allocator, you need a way to put your data. So libpmem, so this is the one, libpmem, right? It supports all the local persistent memory APIs for you to write into the persistent memory, and low level support for remote access to persistent memory. So this is like bringing in the high availability. You have one server where you write one copy, and if you want to write to another copy to another server, so that's the library that you have. So it's pretty much, you have the APIs to utilize. Now, and similarly the other things, libpmem log, anybody with the database world, you can use the write-height logging with the persistent memory and libpmem object. If you are from the world of archiving objects, billions of objects, that's the lib you should be looking into. And there is a block interface also. So these are all that are developed over a period of time, and these are the new ways of programming with your applications to take the benefits of this fast media, right? So this is slightly different, like moving away from POSIX, you're directly calling these libraries. These libraries are attaching to your application, and seamlessly you start using them with the APIs. Okay. So this is something new, libpmem KV. It's a key value store. This is still experimental, and if someone, key value stores are being used quite often in the new world of databases, right? It's becoming very prominent that just put and get from storing the data, it's more popular. So these are some of the new libraries that are being written, and you can take a look at that also. So typical, let's say that if you have all these things, the way I showed you all these models, all these different libraries that are available. So here is one stack, example stack for changing the Cassandra, which is a NoSQL DB, right? And Cassandra uses a lot of Java code, right? It's completely written in Java, and Java transactions, allocations are done. So below the LLPL, you have this libpmem object and the libpmem memory. So these two libraries will give you the same abstraction. And you can, below that is a persistent memory where you can directly write it. So this is one of the sample stack that you could utilize. And so this is some of the learnings. There are, as I said, I told you that there are different ways of using the persistent memory. Being backward compatible, where you can still use a POSIX model, and move away from that to a model where you are directly using the persistent memory. Okay. Yes, they have been optimized for that. Yeah, those are the ways to use it. They have been optimized to handle persistent memory. So in typical, one of the things earlier world, when you had CL flush, right, like it's a single instruction that does flush from everything from your cache, right? So in the old model, we had, you did couple of changes and you did CL flush. The CL flush is supposed to flush all the data that was there in the CPU L1, L2, L3 cache to the persistent memory. Now the downside of this is that it empties your everything, whatever that is, invalidates whatever that is there in your L1 cache, which is little bit hurting, because when you invalidate your CPU caches, right, you lose some data that you would like to access in the near future. But all these things, libraries use those newer instructions, and they are optimized for all these new instructions which Intel has already released. Some of the instructions which are very much meant for persistent memory. So all those things are there. So you don't have to bother about the intricacies of all those things. You use it as a standard API. It's been made a little bit easier. You bother more about the improving your logic rather than the system problems. Right? Yeah. So with this, where are we heading towards? We are heading towards a world where what's the POSIX equivalent for persistent memory? If I ask you, today we are all very comfortable with using POSIX APIs, right? We blindly use it because we know that it will work. It's been there for quite some time. You create a file, you write a file, you close a file. This is all POSIX. So what's the equivalent of that kind of interface in persistent memory? So this is where SNIA is also heading towards. Make it easier, either in kernel or library features that I showed you, and transparent to app. App shouldn't be bothered about that there is something called flush I have to do to persistent memory. All I know is that I will create an object, I'll write the object, and I'm done with that. And behind the scene, it should be like a transactional handling, right? More higher level abstractions, easier to program. So these are some of the things. So the other things are like the availability of transactions, libraries, and different language integrations, and fast remote access. So this is happening, remote access to the persistent memory has been happening in the recent few years, where you want to get a high availability servers for your applications, right? Writing to one server is not good enough. Like if that server goes down, if it doesn't come out, if it doesn't come up, then all your persistent memory is locked into that memory, right? So you want to write it on a separate another server. So that's handling a typical high availability use case. So that's a fast memory access. And remote persistent memory has some challenges. It's and some of the definitions are here, like NUMA. It's when you have memory going across a network, right? It's by default it's NUMA. You know that if I access locally, I'll have fast access, but if I go to on the network, it will be slower. So you need to be aware of that. It's kind of a NUMA programming, and network introduces some unavoidable latencies, and transaction model will often favor pull versus the push operations. So you will have to treat local persistent memory different from if it is available on the remote servers. That's the point. And this is one of the examples that I told, how you can benefit if you have application, how you can benefit from the persistent memory by utilizing these libraries. And here is one of the example. I'll quickly move to the Cassandra example here. This is again saying why can't we use it for Cassandra. So this is a Cassandra write path straight away, right? You have data coming in, you have a commit log, it's a mem table is volatile, and you have commit log which persists the log data that is there, and then you have a SS tables that going to the disks. Now if you want to replace this with only this, right? You have data coming in and you write to the persistent memory storage. That's it. No commit log. Your persistent memory itself is a commit log, and that itself is the SS table. Any commit that you do, any write that you do, it takes care of both commit logs and even persisting it onto the SS table, right? So we have moved from that world to this world. This is possible. So that's the power of having persistent memory. And here is detailed explanation as to how Cassandra read path could benefit from this, because everything is in memory and you don't have to go to the disk, right? In Cassandra, when you do, if you use it as a time series database, right, and when you do a search across a timeline, you'll have to go through multiple data, right? And if the data is on the disk, definitely your reads will get hurt. And everybody knows that Cassandra is very good at writes, but not at reads, because reads may go down to the disk. It may not be in the memory. And if you do a range scan, if you do, definitely you will hit the disk. And that's where suddenly you will see that Cassandra is behaving something very vague, and the latencies will keep increasing. So this is a way to avoid all those problems with the if the data is coming from persistent memory storage, the responses will be fast. And this is the architecture. I'll just highlight here that the yellow box, what you see is there is the low-level persistent library, and Cassandra has its own persistence engine within the code, and that can be using all the libraries that are there for the persistent memory, like libpmem. And Java, and then persistent memory development kit, that's the URL, and you could use all those libraries that are available for you to write it over the persistent memory. So this is a typical way of utilizing the persistent memory with these objects. And here are the resources from SNIA. All the resources are there, and if you are looking for that PMDK libraries, they're all on the GitHub, right? I have 5 minutes? Yeah, sure. So I'll just touch upon, because I talked about persistent memory, now interesting topic is computational storage. How different is this, right? Here we are talking about, uh, uh, the premise here is that data capacities are increasing, okay? And the compute capacity is increasing, but is the architecture that is accessing that compute is any better, or do we have the bottlenecks? What is that I can do to improve this? Is there a way that if compute can go to the data itself rather than data coming to the compute? In the persistent memory world, when you are accessing all the data that is there on the persistent memory, it is going to the CPU, right? To processing. It's the other way. It's going, data is going to the compute. But is there a way that compute can go to the data? Now, why do you think that this is interesting? So, here is the central process. This is the typical von Neumann architecture, right? What I told, the CPU is there, and then you have storage data coming to the CPU. Now, in the computational storage, right? This is the difference is that, let's say that you have a compute that runs on the storage itself, right? That's a difference, big difference. That you don't send the data, but the compute comes to the data, and you process the data and give out the results. Now, how this is all looks nice on the hardware, but as a software developer, how should I differentiate? These are some of the differentiators, right? When to use computational storage, you have large data transfers being done, and PCI itself becomes a bottleneck, and 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 the same thing as if we have a way to send our logic to the storage, then you could run it on the storage itself and do the computational. And when to use the NVDIM, you have compute heavy, and you have lot of small transfers that are happening to the CPU. It's not a big transfer. It's typical in any OLTP transactions, right? Lot of transactions, millions of transactions happen, but they're all small, right? But when you go to the analytics world, you have a lot of big data set, and you have to crunch that data in a few minutes or even few seconds parallelly. And inherent parallel nature is there in your compute, in your data that you could crunch. So that's where the computational storage becomes more important. It kind of looks like a, it kind of looks like a tier, but here only the difference is it's a distributed computing now, rather than having a centralized way of computing where all the data comes to one place and then you process it. Now, rather than doing that, you give out those tasks to the independent distributed compute that is available on the storage itself. So multiple people doing that same task parallelly, and that's where you will boost your performance, right? And here, these are the taxonomy, computational storage device. The computational storage device is the one, so this is the traditional model, right? This is the traditional model where you have storage, and here is the computational storage processor, which is sitting on the your storage device, and here you have two, both of them together, storage and the computational storage processor. So this is what we are talking now, and then you have the other models where entire storage array has computational storage drives itself. Every drive has a compute within that. So these are some of the taxonomy that's being defined, and anybody want to go beyond this point? What is that we have to do? A common nomenclature. When we say computational storage processor, means it's a processing, it's a compute. And when you say computational storage, then you have both of them, processing capability and even the storage. And these are some of the possible architectures. It's a FPGA to multi SSD architecture, where you have FPGA that's working with all the flash modules. This is the compute, and here you have FPGA talking directly to all the flash and the RAM, and this is only FPGA only architecture, and this is a IS6 solution. So basically, you are adding more capability within the storage devices with the compute being there available. Now what's important here is how do we access that? These are the new things, right? You will have to define a common API, and that's where SNIA is working into define these APIs, okay? And so this is some of the things, because the computational storage twig has been recently started. Any industry vendors who are interested in contributing to this, please join this twig, okay? And here are some of the SNIA URLs where you can find a lot of more information, okay? Yeah, that's all I had on where one way to look at it is, as a programmer, how do I exploit that? Typically, analytics workloads have inherent parallel processing of data, right? I want to process this data parallelly, and they are sequentially, they are not, in the sense, there is no dependency on each of the data's output.
Yeah.
Like if I want to average the data over billions of records, I can do it part by part, right, and get the results. But there is no interdependency. If you have a workload like that, where lot of data is being transferred, computational storage is the way to go. In the sense, you should look for that. That's the architecture. And if you have lot of small data transfers going to the CPU, and there is an interdependency on, when I do this, the next result is dependent on this, typical like a transactional workloads, right? I want to make sure that this data goes there consistently. That's where you look for persistent memory.
So CPU usage may be considerably less in cases of computational storage
CPU is only involved in initiating the tasks.
tasks.
And the
Scheduling.
computational storage, where the compute is available, he can continue start working. He can only get the results back.
Okay.
So he is not involved in processing that data itself.
Only scheduling.
Yeah, maybe, yeah, just the scheduler. He becomes the master, and then the rest of the guys could get the data.